Hello, everyone. Thank you so much for joining the session today. My name is Imad Mohammad Khan, and today I have with me Kaushik Chilamkurti, who will be the speaker for the event today. Let me tell you the agenda for today's session, and then we can kick off the session. So right now, I will introduce the speaker. I will also talk a little bit about what Mantis Data Science webinars are, and perhaps a small introduction about myself as well, and then hand the mic over to Kaushik. He will take you through the sessions. He will take you through the session, and towards the end of the session, we will have question and answers. So you can drop your questions in the chat section, or there's also the question section in this platform. So you can decide how you want to drop your questions. Kaushik will decide if he wants to take them during the session or towards the end of the session. Towards the end of the session, I will be there to facilitate it anyway. And a little bit about Kaushik right now. So Kaushik graduated from IIT Madras, and he's currently working with the Ola Electric Autonomous Driving team as Senior Research Engineer in Reinforcement Learning. Before joining Ola, he worked in algo trading startups and deployed RL agents. He's an avid blogger, and he's published close to 50 blogs in game theory, NLP, RL, and temporal models. Thank you so much, Kaushik, for agreeing to do the session. We are very happy to have you here today and looking forward to learning a lot from you. With that said, over to you.
Sure. Thank you very much for the brief introduction. So let me jump right into the reinforcement learning part. So I have my slides. Let me just start sharing them. Right. Yeah. So yes. Well, reinforcement learning, I think, is undoubtedly the next biggest thing in AI. And the idea of this session is to basically dumb down this complex and intricate reinforcement learning, mathematical formulations, and I believe the aspiring data scientists, researchers, and technical managers benefit the most from this session, right? So in this session, we'll try to understand what reinforcement learning exactly is. We'll try to point out some differences between reinforcement learning and the standard supervised learning methods we see. And also the objective of this talk is that you will be, end of the day, you'll be able to identify and fit a particular problem in the reinforcement learning paradigm, right? So let me just move to the slides. Yeah, he gave a great introduction about me, so I'll just skip that, right? So what exactly reinforcement learning solves, right? So before jumping into the very intricate definition, let me just start with my simple intuitive based definitions, right? So reinforcement learning essentially deals with solving sequential decision making problems, right? So, and let's try to elaborate this word, sequential decision making. Let's try to break this, and then we'll try to understand what exactly this word is, sequential decision making, right? So let's take the word decision making here, right? So whenever, let's say, for example, if you're shown an image and asked to tell if it is a cat image or dog image, so that's exactly decision making, right? So, and as you are aware of the classification models we see, the standard CNN models, they essentially try to achieve the same thing. You feed a lot of images of cats and dogs, and at the end of the day, you predict whether it's a cat image or a dog image. So these are classification neural network model, which is used for decision making of whether it's a cat or dog, right? So that's a simple decision making, and it happens in almost every classification problem we see or regression problem we see in the standard machine learning, right? Now let's worry about the word sequential in the sequential decision making, right? That is what exactly reinforcement learning solves, sequential decision making, right? So when you have a series of decisions that essentially define your success, not just one move, but sequence of moves which help you define your success, right? So one standard example is a chess game, right? Let's say you're playing a game, for simplicity, around your opponent is a computer, and not just one move, but sequence of moves decides your fate, decides your success, right? So you need to take a appropriate move at every opportunity you get, and all those moves essentially make sure that you win a game, not just one move, but sequential of moves, right? So as I said, a series of such moves will help you win the game, not just one move, right? So that is what exactly is sequential decision making. So you need to take a decision at every point of time, and the sequence of such decisions will end of the day will help you win the game or will help you reach the objective, right? So reinforcement learning essentially solves this problem, not just decision making but sequential decision making, right? So as I said, reinforcement learning essentially deals with sequential decision making. I know that I'm overemphasizing on this, but this is very important that you understand that reinforcement learning essentially solves not just a single decision but a sequence of decisions, right? So and as I mentioned in the chess example, we essentially have an objective. In the chess example, it's essentially the objective is that you win the game at the end, right? And when you're, for example, when you're driving a say when you're agent, when you are driving a car, the objective is to reach the destination safely, right? So essentially this goal we are talking about is, I don't know if I reached a ping. Okay, the goal we are talking about is basically encoded as an objective in the reinforcement learning system, right? So, and as I mentioned, reaching your goal typically it involves a series of actions in a sequential order, right? Now let's come to the definition of reinforcement learning, right? I hope you understand what exactly is sequential decision making, and let me start with defining the actual definition. So essentially, there are many definitions available in the reinforcement learning literature, but I think this is the one which I like the most. So let's start with this. Reinforcement learning is a subfield of machine learning that teaches an agent how to choose an action from its action space. It interacts with the environment in order to maximize rewards over time. I know it's complex enough. So again, as we did for the sequential decision making definition, let's try to break this in simple words, right? So in here we see the word environment. So let's start with that. So the image you see in here in the slide, it will come again and again and again in the upcoming slides, or in any oral literature you see this image very often, right? So let's start with the word environment, right? So environment is essentially the world in which the agent performs action, right? So environment essentially produces information which describes the state of the system. So the environment could be a simulation. Environment could be anything, a real life or a combination of both. For example, in the autonomous driving space, which I'm working on right now, we essentially have in both simulation and the real world. So in the simulation, we have something called a Carla simulator, where we have a simulator of the real world car, right? And we essentially have all the control, everything can be encoded into the simulator, and we train an agent on top of that simulator, right? So environment can be a simulator or real life, or it can be both, right? So for example, in the chess example, the environment is essentially, as I mentioned, it's the embodiment of how the world works, right? For example, in the chess world, it's essentially environment consists the rules, the underlying rules, how the chess game works, right? So for example, if I move a pawn, if I move a horse to here, then essentially the computer moves another pawn, right? So then there is an actually change in environment. There is actually change in the state, right? So all these rules, for example, the horse can move in only one particular move, and for example, the soldier can move in only one particular direction. So all these rules essentially comprise the environment, and don't get too confused. Like we will try to mathematically give a structure to the environment in the coming slides, but let's just understand that environment is essentially a manifestation of the dynamics of the world, or it's just software or some kind of code that explains how the world works, right? So let's just hold on to this definition for a minute, and then once we go to the mathematical formulations, I think you'll understand the word environment more better, right? So now coming to the same definition, we have the word agent, right? Learning that machine learning that teaches an agent how to choose an action. So let's worry about the word agent, right? So agent is basically a program you train, and the aim of the agent is to do a job you specify, right? And it's basically agent is given an objective, and you essentially need to train the agent to reach that objective. An agent takes an action in a sequential manner, right? For example, the objective of the agent in this chess game is to win the game against the computer, and at every opportunity it moves a pawn, and that's how it essentially reaches the objective of winning the game, right? How do we view the objective? uh, Before that, let me just walk you through what is exactly actions, right? So as I mentioned, the agent needs to act on the environment at every opportunity, right? In this chess game, it's essentially you can move different pawns in the at every opportunity it get. That is what actions is, right? Actions basically it's a move made by the agent on the environment, right? And how it moves, how it acts is basically uh, from what it observes from the environment, right? So it observes something called observation or the state from the environment. So in this, if you look at this iteration, whenever it does an action, it essentially gets a state, right? And it get to act on that state, and then it takes in another action, right? So essentially, as you can see in the example, action is basically at every point of time, whenever you get an opportunity, you can move in pawn. And one important thing you must understand is that actions, there are only limited legal actions. We call it legal actions. For example, you can't really move the horse pawn in a different direction. It has to move in a L shape, right? So there are legal actions. You can't take essentially every action you want. That is the first note you'll need to take home. The second one is whatever actions you take, it needs to cause a change in the environment, right? So for example, if I move the pawn to here, actually the environment changes, because in the next opportunity you get, the computer might have make a move, right? So the state actually moved. So that is one important thing when you're designing an action, or when you're designing in actions. You need to make sure that it actually have some considerable impact on the environment. So these are the 2 points. One thing, the action has to be legal. The second thing, the actions has to make a change in the environment. And the final thing, I've been keep on telling that agent gets an objective to, at the end, agent get to solve a goal, right? So how do I encode that goal? How do I give that goal to the agent? That is through rewards, right? So rewards are essentially at every time step. Whenever you take an action, you get a reward for that action, right? If you take a bad move, you essentially get a penalty, negative of reward. Or whenever you take a good move, you take a reward for the good action you took, right? So usually the reward signal is a numeric. It's just a numeric, and then it needs to be reinforced in behavior, right? When I say reinforced in behavior, for example, if there are two actions, and if the two actions are but one action is better than the other action, then the reward you get for the better action should be more than the lesser action, right? So it has to be reinforced in behavior, right? So let's just try to complete the definition now. So you have an agent. It's just a program. It's just a simple software which gets to act on the environment. And how it acts is basically looks at the environment state, right? It gets to looks at the environment state. It gets to take an action on the environment. This environment, whenever it acts on the environment, you get a change in state, because as I mentioned that it needs to change the state of the environment. And then for that transition, you get a reward. And this reward essentially tells you whether whatever action you did is a good action or a bad action. So this is what exactly, sorry. Yeah. So this is what exactly a reinforcement learning feedback loop looks like. This is how a reinforcement learning loop looks like, right? Now let's try to I'll try to give an example to help you understand how to define a problem as reinforcement learning problem, right? So now that we formally defined what reinforcement learning comprises, so in any RL task, reinforcement learning modeling task, it's very essential to define what exactly is environment and what is agent, what is a reward, and what is the actions. These are the four important things. If you have a problem, if you could define these four things, then you essentially have a RL problem at hand, and you can solve that problem through different methods in reinforcement learning, right? So this is a very famous example called cart poll. It's a very simple reinforcement learning example you would come across every time you start learning reinforcement learning, right? So let me explain you this task. So in this task, a pole, as you can see, there is a pole is attached to the cart. This is a cart, the black square rectangle is the cart, is called cart, and this cart can be moved on a rectangular task on a frictionless track, right? So, and you can move this platform either left or to the right. Like you can just move this platform, and the goal of this environment is that you want to make this pole upright. You want to balance the pole, right? I mean, if you remember, we used to play in the childhood that we'd want to make a scale or something on the set. We just want to move such a way that the pole is straight, right? This is essentially a simpler game of that sort, and at every point of time you can just move the cart to the right or the left in order to balance the pole, right? Now let's try to define all the definition, all the concepts, all the notions we learned in the previous definition, right? The objective is to keep the pole upright. That's the simple objective. And the state is basically, you basically have some numbers related to the pole. Like you'll basically have a cart position, you will have the cart velocity, whether it is moving to the right with what velocity, and the angle of the pole. If the angle is straight, then you basically have a 90 degrees. If the angle is like towards the, if it is at to fall, then you basically have 90 degrees as the state, right? And the pole angular velocity, how what is the angular velocity of the pole? So these are the four vectors that the agent get to observe from the environment, right? And the action is essentially whether you can move the cart to the left or to the right. So that is basically the action. And as I mentioned in this in earlier, that you get to always define an objective through rewards. So rewards are essentially some kind of proxy to the objective. If you look at the objective is to keep the pole upright, right? And the reward, whenever in every time step, whenever you manage to keep the pole upright, you get a +1 reward, right? And let's say if the pole fall right away, if the pole actually fall away, then you basically give a huge negative reward. That's when the episode ends. So that's when you stop the experiment and you begin new, right? So this is how we essentially define a problem in the reinforcement learning, right? So I hope this example is clear. You basically have objective where you want to keep the pole upright. You have a state where you basically observe how the pole looks like, whether it is upright, what is the velocity, and so on. You get to do an action, whether you can move to the left or the right, and every time you manage to keep the pole upright, you get a +1 reward, right? So these are we define a problem, and then let's look at another example. And so basically in this example, you have a humanoid robot, and the humanoid robot is supposed to run on a planks and avoiding the gaps in between, right? Looks like some kind of Mario game or something, right? So basically the objective is to make the robot to reach the destination as quickly as possible and not to fall in between, right? The state is basically just look at the pixels from the robotic eye, right? You just attach a camera on the robot's eye, and then you let the agent to see that camera. And the action is basically you can move each limb by theta angle, right? Here in this case we have a lot of actions, right? You have 4 limbs, and then For 4 limbs, you have a lot of joints, right? So, and you can move the joint by theta degrees for all the joints you have. So the action space is huge, and the reward is basically if you reach the destination, you get a positive reward. If you fall in between, you get a negative reward, right? And as I mentioned, the environment is basically all the Newtonian laws we know, right? So that the real world simulation, all the gravity, laws of motion, that embodies the environment. So this is a very famous paper where they try to use reinforcement learning in the robotic setup, right? So other than whatever examples I've shown, there are a lot of use cases for reinforcement learning in solving business problems, right? So we have, as I mentioned, there is a use case in robotics where there is a huge manufacturing supply chains, and then we could teach actually reinforcement learning to act on a particular item in the supply chain, manufacturing supply chain, right? And the next biggest application right now, it's trending, is on the finance space, right? I came from the finance background where I tried to deploy reinforcement learning models in the actual trading setup, right? And it's really important to understand why reinforcement learning is suited for a finance kind of setup, because I mean, as I mentioned in the session, in the earlier part of the session, that it's not just about taking a single decision, but you essentially get to take a sequence of decisions, right? That is what exactly makes finance well suited for RL paradigm, because it's just not one decision which will help you improve your returns, but series of decisions on a daily basis. You get to take a series of decisions, and a quality of such series of decisions will help you maximize your goals, maximize your portfolio, maximize your or minimize your risk, right? So, and one of the important factors which I'll overemphasize in the later of this session is that reinforcement learning not just looks at the immediate goal, but also tries to maximize your future goals, right? So that is one of the reason why reinforcement learning is very well suited for the trading problem, because you just don't want to maximize your returns tomorrow, but you want to maximize your returns by the end of the year, by the end of the month, and so on, right? Coming to the other applications you have in the traffic control, reinforcement learning, people started using reinforcement learning a couple of weeks back. I was actually having discussion with few government agencies, people working with government agencies. They want to implement reinforcement learning for traffic control, right? So vehicular movement and traffic control. So reinforcement learning, the actions in this case, it would be good to see what exactly can be the actions. The actions could be could be that at every point of time, maybe at every 1 minute or every 30 seconds, you get to choose which lane to allow and which lane to close in the traffic intersection, right? The other couple of business problems I came across is in the data center cooling systems. So Google, Facebook, these guys are actually trying to use reinforcement learning for the data center cooling, right? At every point of time, you want to understand how you want to actually cool your data centers based on the load you see, based on the load the agent observes, and so on, right? That will basically help them, and the objective of that task is to basically reduce their end of the month current bills or something like that, right? So these are the few business problems I've come across, and there are numerous business problems in the space of supply chains, in the space of educational tech, ed tech, and so on, right? So as I mentioned in the beginning, that we'll try to bring from formalism to the reinforcement learning paradigm. So let me just rewind what we have learned. Let me just walk you through the iteration once again before I give some mathematical formulations to what we just learned abstract in the previous slides, right? So you have an agent observes a state that comes from the environment. State is basically the state of the environment, and you get to take an action. that basically makes the environment change. That will basically, once the environment has changed, you have a new state, and the new state the agencies, and in this iteration, every time you act, you basically get a reward which says whether you take a good action or a bad action, right? And so, as I mentioned, we'll try to bring formalism to this abstract things here, right? We'll try to bring formalism, and I think that is the best way to understand this reinforcement learning paradigm, right? So, one second. So far we learned reinforcement learning in very abstract words, and we'll try to give mathematical structure to this environment. So you might have heard something called Markov chains or Markov decision processes during your lecture series. If you haven't, that's fine. I'll explain it in very simple words. So I think it's time to unravel this Pandora's box of the most infamous mathematical formulation that changes the way we looked at science in many scientific fields, actually, right? So I want my readers to put the whatever environment definition I gave, just put it aside. I'll try to give the mathematical formulation for this MDP, and then we'll come back and connect the dots, right? So I'll try to spend the next 5 or 10 minutes on explaining the MDP, and yes, let's start. So basically, MDPs are known. They're as old as linear regression, right? MDPs are known at least as early as 1950s, and they have applications in almost in many disciplines: robotics, automatic control, economics, and manufacturing, right? So let me try to help you understand how MDPs actually works in environment, right? So let me just help you understand with a simple example, right? So let's just talk about my world, right? I will talk about how I work, how I function myself on a daily basis. So I wake up in the morning, I go to work, or if I feel lazy, maybe I go to sleep again. And when I'm working, I either go to lunch or directly call it a day and go back to sleep again, right? This is just a simple way how I work. I'm just joking. This is not how I work, actually. For simplicity, I'm just assuming these are my world works. These are my function, right? And I'll help you understand how MDPs actually help you on approximating my world, right? So basically, in this, as you can observe, I can be either at work, or either at sleep, or either at lunch. So whenever, at any point of day, I find myself either at sleeping or working or eating at lunch, right? So now let's try to visualize them. Like I want to have some structure to visualize them, right? So if you closely look at my world, there is some randomness involved. Like if I am lazy, then I go to sleep again. If I'm not doing well, then I'll go back to sleep again, and so on, right? So there is some stochasticity involved in my world, right? So if I call this sleep, work, and lunch as states, because these are the 3 states I find myself at any point of time, there is a transition involved between these states, right? For example, if I'm at sleep, with 30% of the probability, I go back to sleep again, right? And with 50% of the probability, I go to work. With 20% of the probability, I just go to lunch again, right? So what I'm trying to do is, with probability, I'm trying to model my stochastic world. So there is some randomness involved, and I'm trying to use probability to figure out the randomness, right? For example, if someone is logging my interaction, logging how I move from sleep, work, and lunch for, like, let's say 1 whole year, and then if they try to understand like how many times I'm actually waking up from sleeping, I go back to sleep state again. From in 30% of the times I do that, then the probability of moving from sleep to sleep is 30%, right? Then if the probability of moving from sleep to work is 50%. So these are, I can just do a Monte Carlo search, and I can try to find these probabilities, right? So these are ways I can simply model my world, right? So if my model is simple, then I can simply model my world using this simple formulations. And if I have to even use some more mathematics, I could use some matrix manipulation where if I can put rows and columns as my states, and this number basically tells how I am transitioning from sleep to sleep, right? For example, 0.3 from sleep to sleep, there is 30% probability. Like transition from sleep to sleep state with 30% of a probability. And if I transit from sleep to work with 50% probability, sleep to work 50%, this number basically tells that probability number, right? So this is a simple transition matrix. We call it transition matrix. It basically tells what is the probability of transition from one state to the other, right? So these called transition probability, right? So if my world is this simple, these are I simply figure out mathematically pin down my world, right? So this is what exactly is Markov decision processes try to achieve, right? So you basically you basically tell what is the next state, what is the probability of transition to the next state given I am in this state, right? For example, from work, 30% of probability I go back to, sorry, if I'm in state sleep, with the 30% of probability I go back to state sleep again. With 50% I go back to work, and 20% I go back to lunch, right? So Markovian property essentially assumes that the transition to the next state only depends on the present state, right? So that is what exactly Markovian property is. So that is why we call this as Markovian decision process, because it tries to simplify the way my world works, right? So essentially, the Markovian property is very simple. Markovian decision processes are very simple. You basically have a finite states, and it tells you what is the probability of moving from one state to the other state. With simple matrix formulation, you can just write it in you can call it as transition matrix or transition probabilities, right? This P is essentially the transition probability. So essentially the environment what we've been talking is the transition probability, right? It's basically the MDP structure we just gave. That is what exactly is environment. So as you can see here, on top of state you also have something called action. So what it basically tells is at every state if you take an action, you will get a probability of what the next state looks like, right? So the state st plus 1 depends on the state tst and the action you take at the state st, right? So I'm skipping this part because it is out of the scope of this lecture, but you must understand the fact that the environment which we've been talking in the abstract words is being mathematically pinned down using something called MDP, Markov decision processes. And in the heart of this Markov decision processes, we have something called transition matrix, which tells you how a state transits from one to the other. It gives you a probability, right? So as you can observe here, once we talk about probabilities, we essentially talk about the stochasticity. So whatever environments we see, there is some stochastic nature involved, right? For example, just to give an example, so for example, these one state, right? I made a move, and the next state, the computer has a lot of steps, lot of actions to do. So it can actually move this one, it can actually move maybe its own horse, and there are n number of states possible, right? So these one of the state the computer took, but there are lots of states possible once I take this action, right? So there is a like, let's say there are 100 different actions. You basically have a probability to those 100 different actions, right? But the computer actually took this particular step, and these are the next state looks like. But it is also likely that it can actually move a horse, right? This is what the stochasticity involved, and then reinforcement learning is known to handle the stochastic environments. Right. So I hope you guys understood how we mathematically formulate this environment using something called Markov decision processes. And at the heart of Markov decision process, you have something called transition matrix or transition probability, which tells you how a state moves from one state, how a state moves to the other state based on the action you take, right? And it's a stochastic environment. So, and we've been talking a lot around rewards, right? And I would want to give a simple formulation to rewards as well. So basically, whenever you move from one state to the other state, you basically get a reward. Simple, and it's essentially called Markov reward process, and we call it Markov reward process because the Markovian property remains same here. The reward you get depends only on the current state, right? So why I've been focusing too much on the Markovian property, because the next state or the reward you get from this state always depends on the current state, right? So it is very, very important for RL practitioner to know this property, because the current state should be informative enough to tell what the reward looks like or to tell what the next state looks like, right? So it is very important to design a state space. So in reinforcement learning, as a reinforcement learning experts, we struggle a lot. We spend a lot of time to design the state space, how the state space would look like, whether the state space is informative enough to tell the next state or not. And whenever you break this Markovian property, the whole reinforcement paradigm falls apart, right? So these very important note I would want to take home, because it is very important in solving the business problems in designing the state space, right? So as I mentioned, the rewards is one way to pin down the objective you have. In the chess game, the objective is that you want to win the game. In the card pool example I explained, you want to keep the pool upright for the 200 steps, right? Then how do I use the reward? How do I use the reward function to essentially give an objective to the agent, right? So here we'll just try to go a little bit into the math, and then I'll try to explain how an objective can be written using, or how the objective can be defined using rewards, or how the rewards can be defined using the objective, right? So let me just give a small example in my own professional experience. So I was, as I mentioned, that I was working in the autonomous driving labs. So one day I was actually writing an agent to drive a car, and the reward I gave to it is whenever it moves ahead, whenever it moves without making collision, then I give a +1 reward. That is how I wrote a simple reward function I wrote. And then agent became naughty, and then it figured out revolving around itself will maximize the reward, right? Revolving around itself, whenever it revolves around itself, it avoids collision, because it just have to move in circles, right? And whenever it moves in circles, it just get +1 +1 +1 reward. So it's the point I was trying to make is it's very important to encode your objective. In my case, the objective is to reach the destination, but the way I designed reward, the agent figured out revolving around itself should do fine, right? So it's very important for RL practitioners or aspiring RL students to understand how to define a reward function. So that is very important, and I would want to overemphasize that, right? So in the reinforcement learning paradigm, let's try to fit the rewards here, right? How rewards can be used to define an objective. So basically, as I mentioned, there is an interaction. You have this interaction loop, state space. First, the agent sees a state, takes an action, it gets a reward in return for the action it took, and then that changes the environment to the next state. And then once the agent sees the next state, it takes the next action, and then for the next action it took, it gets the next reward, and so on and so on. So this is the sequential decision making I've been talking about. You get to choose A1, A2, A3, and so on, right? And the objective of the agent, so the agent essentially sees only R1, not R1, R2, right? And then the objective of the agent is to maximize this R naught, R1 and R2 and so on, right? It has to maximize R naught plus R1 plus whatever reward it accumulates at every time step, it has to maximize that. So that is a reward. That is the agent's job. Agent's job is to maximize the rewards at every time step, and our job is to give the rewards in such a way for the agent to learn. It has to maximize the objective of the game, of the problem we are solving, right? So for the chess game, you don't get rewards at every time step, but you get a reward at the end. Once you win the game, you get a reward. And the minute you lose the game, you get a huge penalty, right? So the agent job is to not just maximize the reward it gets at that point of time, but it has to maximize the reward throughout the interaction, right? So as I said, the agent interacts with the environment by observing the state, and using this information, it selects an action, right? So so there is okay, let me just skip this, we're running out of time. Okay, so as I mentioned, the objective of the agent is to maximize the rewards, and in the agent iteration loop, you have this rewards, and this goal is essentially the not just the sum of rewards, but discounted sum of rewards, right? We essentially have something called gamma, which is the discount factor, which is very important parameter in the reinforcement learning, very fundamental to reinforcement learning. And this discount factor is essentially tells you, if you see here, R naught into gamma power 0, which is 1, R1 into gamma power 1, R2 into gamma power 2, and so on, right? When if you keep the gamma is equal to 0, the agent tries to only maximize the immediate reward. It tries to maximize this J of trajectory. Trajectory is basically this whole trajectory, the whole iteration loop. The whatever reward it gets from the this iteration loop comes under this trajectory. And if you keep the gamma is equal to 0, it only looks at the immediate reward. The agent looks at only the immediate reward. That is what it tries to maximize. But if you keep gamma is equal to 1, it equally values the immediate reward and the reward that comes after 100 time steps of infinite time steps, right? So gamma variable is very, very important. It tells you how you value your future reward, right? For example, if I'm in the chess game example again, I actually see a reward at the end of the game, right? All this R1, R2, R3 will be zeros, but the end, maybe after 100 time steps, let's say if the game is ending, at the 100th time step, I get a huge reward, right? For winning the game, or for losing the game, I get a penalty, right? So then I'll need to keep the gamma is equal to 1 because I values the future reward equally, right? I value the future reward the most, and I keep gamma is equal to 1. Gamma is a factor which varies from 0 to 1. And then you basically for problem statement to problem statement, the gamma varies, and gamma is a very important factor which basically influences the behavior of the agent itself. How the agent behaves, how the agent takes the moves at every time step is greatly influenced by the gamma, right? So, and we've been talking something on how the agent reacts. That is something called policy, right? Agent, at every time step, agent observes the state and takes an action, right? So you basically have a function that directly maps the state to the action. So that function is called policy, right? So at every time step, you see a state, the agent sees a state, the state is put into this function, and this function outputs in action, right? So this function is called policy, and the job of the policy, the job of the function is to maximize this objective, which is this is what we call expected sum of future rewards, discounted future rewards. This J of t is called expected sum of discounted future rewards. So the job of the agent is to find a policy which maps the state to the action, and the policy needs to maximize this J of trajectory, which is expected sum of future rewards, right? As I mentioned, the policy, we usually write the policy, describe the notation of the policy is pi, and a good policy should generate a set of actions which produce a trajectory that maximize the agent's objective, right? So it's basically in the chess game, the state can be something like a vector which is telling where all the pawns is, and the action is basically, it basically tells what is the next move, which pawn to move, and the pi function directly maps it. And the goal of this pi is to find out the is to maximize this objective function, right? So we've been seeing a lot on the deep RL, deep reinforcement learning. So what exactly is deep, right? So as I mentioned, the policy pi is a direct mapping from state to the action. So the function we approximate using deep learning. Simple, right? Basically, in the beginning, the functions can be something like a linear. In the classical reinforcement learning, the function is something on the linear function. So it's basically action is a linear combination of the state vectors, the vectors and the value in the state. But as the deep learning came into the picture, you essentially have a multi-layer network, or if it is a state is something like an image. In my case, the state in the autonomous vehicle space, the agent looks at the cameras, like you attach 3 cameras, and then the agent looks at these 3 cameras, right? And it has to take an action, like what control to take, what acceleration, what throttle, what braking to do, right? So that I could use something like a CNN, which just maps these 3 cameras images to an action, which tells whether I should take it left, whether I should break it, and so on, right? So, and whenever someone says that they're using deep learning model, multi-linear perceptron, you need to have something called loss function, right? So here there is something called a policy gradient. It's a very mathematical derivative. It's you'll need to dig deeper into the maths to understand this loss function. So just like the point I was trying to emphasize is just like many CNN or binary cross entropy or whatever regression task RMSE, you have a loss function here as well to update the weights, right? So end of the day, if you update the weights using this loss function, you basically get a policy that magically optimizes the objective you give, magically achieves the objective you give. So that is the whole background, the whole understanding behind reinforcement learning, right? So there are lots of algorithms. What we just discussed is something called policy based reinforce. There are some other class of algorithms called reinforce, value based, model based, and then there is some actor critic methods and so on. I don't want to dig deeper into this, but this essentially achieves the same thing. We essentially try to get a policy, and at every time step the agencies, the action, the state takes an action, right? So here we directly try to find the policy. In the value based methods, we try to find something like a proxy to the policy. And the model based methods is basically when you have the model available to you, right? When you have this model, when I say model, is basically both Markov Bayesian process and reward process. You basically have the probability, transition probabilities available. You basically know whenever there is a change in state, you basically know how the reward looks like. If you know all these things, then this model based methods comes into the picture. So this is as old as, again, the model based methods are as old as linear regression. They are very it's basically like statistics of machine learning. It's the model based methods. It's basically rooted to optimal control. They are very statistical. They're very classical methods. So finally, before concluding this session and answering your questions, so there are lots of challenges in the reinforcement learning. The first challenge I encountered myself is non-stationary environments, right? So just like in machine learning,
we have about 8-9 minutes left. So
sure. Just let me wrap up in a couple of minutes. So basically, there are lots of challenges in reinforcement learning. The first one is the non-stationary environments. Basically, whatever agencies while training using an environment, the environment itself can change. Whatever the transition probabilities can actually change, right? So the model you trained while training actually fails in the real world. So the second thing is the reward shaping. As I emphasized, that reward should be a clear proxy of the objective. If you try to give a different reward function, then the objective you try to achieve might be different, right? The third thing is the sample inefficiency. So basically, if you have an cat versus dog example, you basically use the image again and again and again in different batches to update the weights. Unfortunately, that is not the case in reinforcement learning. The sample you got in the feedback iteration with the environment might not be really used again and again. It might make the model unstable. You'll need to create a lot of samples to make the agent good, make the policy good. The reproducibility, because of these generalization issues, because of the sample inefficiency, you will inevitably run into the reproducibility issue. The safety is essentially, when I'm actually using reinforcement learning for driving a car, safety comes into the picture, right? There is a safety is still an open problem in the reinforcement learning, and people are publishing a lot around this space. And the last one is a delayed reward. In the chess game, as I mentioned, the reward comes at the end. You don't get to know how well the agent is doing till the last step, right? This delayed reward and sparse reward is a huge problem in the reinforcement learning. And explainability, just like in any other machine learning algorithm, explainability is still an issue in reinforcement learning. So yeah, so I think I could conclude the discussion with the challenges. So
Okay.
yep.
We have about 7 minutes left in the session.